Welcome back. We're going to look at a classic LeetCode problem. It's a 2-for-2 valid anagram problem. And the task is here to determine if two strings are an anagram of each other. And an anagram is a word or phrase formed by rearranging the letters of a different word or phrase using all of the original letters exactly once. So, for example, if we have the word red and car, no matter how we arrange the letters in red, we are never going to get the word car. However, if we use the word anagram, we can rearrange the letters to this word. And yeah, so I thought I'm just going to show the different ways of how you can solve this problem. So this is, because this is such an easy problem, most people know how to solve this, but if you are starting out with LeetCode, this might be interesting to you. So the first thing you could do is, well, you could just take all of the letters, sort them in ascending order, and then compare the result. So that is one thing that we can do. So if we do that, that's actually quite easy to do in Python. So we're just going to sort the letters in the first string, and we're going to sort the letters in the second string. Then we just compare the two arrays, and they're going to be the same if the order of the letters is exactly the same, and if each array contains exactly the same elements, so the same letters. So that's actually really simple to do. There you go. So in our test cases, it performs well. And when you implement this, you can also submit it to see, how it works against all of the test cases. Now, if you do coding interviews, you always want to give a complexity analysis, both in terms of runtime as well as space. So for this problem, we know, hopefully we know that sorting is done in O of n log n time, where n is the length of the input, so the number of letters in S and T. And strictly speaking, we're also comparing two other arrays, which would add another n. But since n log n is larger than n, we can omit the n here. And now, depending on the sorting algorithm, depending what programming language you use, you can expect that the sorting either has to create a new array, so that would be then O of n time, or if it sorts in place, it would be O of 1 space. However, since here we're taking a string, which is, we're converting it into an array of characters. That's why in this case we have an O of n space complexity. Space. Right, so this is the first way how we could solve the problem. Now, another way we can solve the problem is by counting how many times each different character occurs in each of the strings. And then we just compare the counts of characters in string S against the count of each character in string T. And in Python, we can use something like the counter object. And it's in the collections library. I don't think you have to import it in LeetCode because it's automatically available, but if you don't have it available in your environment, you have to import it like this. And then all you need to do is simply, just return counter. And now we just paste that in, count of S, counter of T. And by the way, it also makes sense to do a very quick check in the beginning. When S is not the same length of length T, we can automatically return false, because we know one string contains more characters than the other, so they can't be an anagram of each other. Yeah, so this is the second approach. And now we are not doing any sorting anymore, so we're actually improving our runtime. We still have to create our array of characters. I think we do. Yeah. Actually, I'm not 100% sure if the string is converted into an array of characters, or if they actually read character by character without converting the entire string into an array. I'm not 100% sure, but it doesn't matter because the counter object itself has to store however many characters we have in our strings. And n equals the length of s plus the length of t, by the way, just to clarify that. Which should be the same because here we're having our little check, right? Or we could say max of those lengths. That would also be accurate. It doesn't really matter because it's linear in the number of characters. So for the O notation, it doesn't really matter. Okay, so now both of these approaches require us to traverse the entire string each time, right? And in both cases, we need O of n space to do so. But what if, well, actually, let me make a small correction. So here, we are actually using O of n space because we're creating two arrays that have the length of s and the length of t. But in this case, we're actually only counting all the different characters. So because the number of characters is actually limited here in the constraints, it consists only of lowercase English letters. That means that actually the space complexity is 1 because it's a constant. 26 characters is, well, it's a constant. So we're actually dealing with content space. So not only did we improve our runtime, we also improved our space efficiency. All right, so now there's another way of how we can solve if we don't want to use sorting and if we don't want to use a counter object that's built in. What we can do is we can just build a histogram. So we're going to do this approach, but we're going to write it by hand. So what we will do is we'll have our little length check. And then what we will do, we will iterate over all of the characters in S and T. And we will basically update a histogram. So this histogram of S is going to be an array of 26 characters, our lowercase English letters. And we will also build a histogram for T. Now, we just need to iterate over the characters in S and T. So I just call this character S and character T let's see. Oh yeah, well, actually we're going to use an index. And because we know that S and T have the same length, we can just pick S here. So the character in S is going to be at position I is going to be SCS. The character at position I in T is going to be stored in the variable CT. And what we now do is we compute the index in the histogram where this character belongs. So, and we can do that quite easily. We could say CS IDX equals, well, how do we convert a character into a number? In Python, there are two functions called character and ort, which gives, so if you put this, you actually get the ASCII code of the letter A, which is a number. I think it's 90 or something. And so if we take this and subtract it from the character at position I in S, then we get a number between 0 and 25, right? Because we just shifted the value so that it's an A. And the next character would be a B, C, after that, etc. So that's how we could do that. And to make it a little bit simpler, we just put that in here. And we can also do the same for T. And now we have the indices where we need to update our histogram. And in the histogram S, at position S IDX, we're going to increase the value by 1. And the same for T. And so that'll build us a whole histogram for each of the strings. And then in the end, we just have to compare them one by one. So for I in range 26, because we know we have exactly 26 characters and counts for 26 characters in our histograms. And then we just do this histogram of S is not, if that is not the same as the histogram of T for the character at position I in our index. So at the 0th position would be how many A's are there. In the histogram position 2 would be how many B's are there, etc., etc. So if that's not the same, we can return false, because it means the strings don't have the exact same number of that particular character that's represented by the position I. And at the end, we could return 2. Now this is a little bit, I would say, messy. We could simplify this a little bit. We just need one histogram, to be honest. And then what we just do is we increment it when we encounter a letter in S, and we decrement it when we count a letter in T. And then we just have to check return any, let's see, any in histogram. Wait, let's see a count or count in histogram. So we're going to iterate over all of the counts in the histogram. And actually, yeah. And if any of them is not 0, then we return, let me see. We want to return false if any of them is not 0, right? So if we encounter one that is not 0, this expression will return true, and then this not makes it false. So let's see if I got that right. Okay, it looks right. So yeah. So that is another example of how we could do this. The same as here, but except we don't use the counter object here, and we basically do it by hand. Now, this means we're always going to use 26 slots for that. In terms of runtime complexity, I don't think we can reduce this, but if we say that the alphabet is not limited to just 26 characters, but could be arbitrarily large, we could still limit the space complexity to how many different characters are actually in those strings, right? Where K is a number of unique characters in S and T. Just gonna abbreviate it like this. So in this case, what we'll do is, instead of using a fixed size array, we're just going to use a hash map. And I'm just gonna call it histogram anyways. And it's going to be a dictionary. And we are doing exactly the same as we did before. We're just going to iterate through the entire string S and the string T at the same time, so kind of in parallel. And we're going to say, we're going to simply put the value, well, we're simply going to increase the value if it exists. And yeah, also if it doesn't exist, we also do the same. We set it to 1. So now we don't have to use a fixed number of slots in our histogram. Instead of, we're only using those for which we know characters exist. And also, we don't have to do this indexing thing anymore. We can just use the character itself as the key. So this would be for S and for T. For S and for T, yeah. And yeah, and then we just check for count. Oh, yeah, by the way, we have to, of course, In one case, we subtract 1. And in the other case, we add 1. So, yes. For count in histogram values, because we don't care what the characters are anymore at this point. We just care that the occurrence of the different characters in those two strings is balanced. So, yeah. And you could also use, an expression like this if you wanted to. I just decided to do this explicitly right now. Count in. There you go. So yeah, so this is another approach. And now we have 3 approaches. So the main purpose of implementing it in different ways is to give you a reason to talk about it, I suppose, and to practice talking while you code. I find myself sometimes starting to think instead of talking. And it's not easy to always have something to say. Sometimes you need to have a small thinking moment. But in an interview, try to talk as much as you can to verbalize your thought process. It's really about verbalizing your thought process more than it is to just fill the empty space. So yeah, that is this easy classical problem. I hope you like it. And yeah, see you in the next one.